Assalamualaikum warahmatullahi wabarakatuh and good morning. Today we will learn about Boolean algebra and digital logic. You can download the lecture on week 4. Okay, so I have uploaded the notes of 2 chapters of chapter 4 and chapter 5. Siapa ni Muhammad Akmal, can you unmute yourself?
Sorry.
Okay, tak apa. Thanks. Right, okay. Before we start for the lecture, so I would like to inform that this course, okay, is one of the course that have an optional for lab where you can come to UTEM, okay, and then had a face-to-face session with the lecturer. Okay, so I would plan to conduct a lab session in face-to-face. Those who can come, those who wants to come back to UTEM, okay, then you can come. Okay, after midterm break. So after midterm break is week 9. So we will start with assembly language. So it needs you to do a programming. So it is better that if you can come to Melaka. Okay, and also those who have a problem with your internet, you cannot say that you have a problem with your internet. You just need to come back here. Okay, so no more excuses for internets anymore. It's because of you are eligible to come back. Okay, so that's one announcement. And then the second announcement is that I have booked the dates for the midterm, which will be on 11, right? So 11 November, 8 p.m. to 9 p.m. meaning that it will be in 1.5 hours, only that time, not the whole day. Okay, so the midterm will be held in online session or in Ulearn. So you will answer the questions and together with the other course, okay, together with the other programs actually. Okay, so it might be congested actually because we have 7 programs that register the subject, and you would have a problem with the internet if your connection is slow. Okay, probably when you try to access it, and also when you try to submit your answer. Okay, so find the alternative. Okay, you must find the alternative. If you have a problem with the internet, then come back. Okay, so that's my advice. So let's start with the lecture. Okay, why is the slide here? Okay, now. Okay, this slide can be accessed through the Ulearn on week 4, and also you can download the lab notes together. It's because of its we will do the lecture and lab together. So if I'm not able to finish it, okay, so I will continue on the on the lab. All right, so okay. Right. Oh my God, sorry. Sorry. Hold on. Okay. Okay, Bismillahirrahmanirrahim. Okay, Boolean algebra. So what is Boolean algebra? Boolean algebra is a mathematical system for the manipulation of variables that can have one of two values. In formal logic, these values are what we consider as true and false. But in digital system or in computer, so these values are on and off, 1 and 0, or high and low. So common Boolean operators include and, or, and not. So this is like a basic Boolean operators. And then they combine it, okay, to become much more complex operators. So the complement represents the inverse of a variable and is indicated with an overbar. So remember when I said first complement and two's complement, right? So the first complement is the inverse. Okay, the inverse of the value. Okay, so usually when we say complement or inverse, it means that it will flip the bits. So if the variable is A, then the complement is A bar, or we can say A apostrophe. So it can be both. Okay, so you will see there's an apostrophe or A bar to show the complement. Okay. Now, Boolean algebra operator can be completely described using a truth table. So the AND operator is a Boolean product. Okay, product, like in other words we call it is as multiplication. Okay, like a multiplication. Or operator is a Boolean for sum. Okay, for sum. And then the NOT operation is most often designated by an overbar. So NOT is what we can represent as a inverse or complement. Okay, so if you look at the operation for AND operator, so this is the truth table. Okay, so 0 and 0 is 0, 0 and 1 is 0, and then 1 and 0 is 0, and then 1 and 1 is 1. So in conclusion, we can see that, okay, so if all bits is 1, okay, then the result will be 1. So that is the nature of an operator. And then for NOT, for OR first. So OR means a sum, okay, OR means sum. But in this case, they don't have carry bits. Okay, they don't have carry bits. So in this case, if it's at least 1 bits, okay, at least 1 bits is 1, okay, at least 1 bit is 1, then the result will get 1. So here 0 or 1 is 1, 1 or 0 is 1, and then 1 or 1 is 1. So that's what I'm saying. At least 1 bit between the variable is 1, then the result would be 1. So that's why they said that this is a Boolean sum. Okay, except that it doesn't have except no carry bit. Okay, it doesn't have a carry bit here. Right, and then the next one is the NOT. NOT operation, as I said, is inverse or complement. Okay, so first complement. Okay, first complement. So they will inverse the value. If the variable is 0, then the result will be 1. And then if the variable is 1, then the result will be 0. So it's very important if we do not have the NOT logic. Okay, NOT logic. Okay. If it's only one operation, then it will be easy. But the truth is that, okay, we have a combination logic. So Boolean algebra, okay, will need a Boolean function. And then from this Boolean function, okay, we will build up the truth table. Okay, we will build out the truth table based on this function. So, okay, so the truth table for the Boolean function x z bar plus y can be shown on this right side here. Okay, so the NOT operator has the highest priority. Okay, so remember, It's because not is the basic one, and that's why we will start the truth table from the not first. Then we will end. Okay, so n would be the highest priority after not, and then followed by or. Okay, followed by or. So in this case, we need to determine which one we need to describe or to lay down the truth table. Okay, so this example shows, okay, since Z bar is the highest priority, then look at the middle column here. We will start with the Z bar. Okay, we will start with the Z bar, and then, okay, we will end Z bar with X. Okay, and lastly, we will OR the X Z bar with Y. This one. Okay, so this is like the last operation that can get the result. Alright, so in order for you to derive the truth table, okay, we must start with a combination, bit combination. So if we have three variables, okay, we call this as variables X, Y, Z, and then so we will list down. Okay, you will list down X, Y, Z, and then the combination bits only will start from 0 until 1. So if you arrange X, Y, Z, so means that Z is the least significant bit. Okay, so it's because it's on the right side, so it will become the least significant bits, the smallest bit. So we will start from the right side here. So 0, 0, 0. Okay, you will start as all 0, 0, 0, 0. And then the bit will increase from the least significant bit. So the least significant bit is on the right side. So from 0 here, we flip the bit, change it, or add one bit, it will become 0, 0, 1. And then next is that, okay, when we add one bit, you add one bit, 1 plus 1, okay, the Z bit will become 0, and then there's a 1 here. And then the next pattern will be 1, 0 plus 1 will be 1, 1. And then X is 0. Okay, and then Z here, okay, YZ here plus 1, you will get 0, carry forward, and then 0, and then carry forward 1 bit. And then when you add 1, you will get 1, and then 0, and then 1, still maintain. And then when you add 1 bit again, you will get 0, carry forward 1 bit, and then there's 1 bit there. And then when you add 1 bit again, so 1, 1, 1. Okay, what happened if we add another 1? So it will become 4 bit, which is we don't have any variable anymore. So we will stop at this. We start at 0, 0, 0, and we will stop at all 1, 1, 1. Right? So if you convert it to decimal, this is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7. Okay? So all combinations, okay, all combinations, all possible combinations is list out like a decimal numbers. Okay, a range of decimal numbers. So start with 0, 1, 2, 3, 4, 5, 6, 7. Right. So now the next part is that you want to find out the truth table for the X, Z bar plus Y. So first that is that we want to find out what is Z bar. So Z bar means you inverse the value. So 0 become 1, 1 become 0, 0 become 1, 1 become 0, right? So this is the result, and then we will end Z bar here, this part, okay, with X value. So if you see 0, okay, X start with 4 bit 0, right? So we know that when we do AND operation, okay, if there is a bit 0, it's always 0. The result will become 0. So here we start with 0, 0, 0, 0. It's because of X here has 4 bit 0, And then we was after that the bit become 1 1 1 1. So and then we can end the bit x with z bar. So 1 and 1 is 1, 1 and 0 is 0, then 1 and 1 is 1, and then 1 and 0 is 0. Okay, so now we will get this result, and then we will OR with y. So x z bar result here, we will OR with y. So follow the bits. If there is at least one bit, then the result will become 1. So 0, 0, 0 or 0, 1 or 0 is 1. 1, 0, 1. And then 0, 1 is 1. And then 0 and 0, 0 or 0 is 0. 1 or 1 is 1. 1 or 0 is 1. So this is your result of your Boolean function. Alright, so this will build up your logic circuits. Okay, it will build up your logic circuit. So if okay, let's how do I want to find my paint. Hold on. Discard kejap. Hold on. Paint. Okay, can you see my did not share anymore. Stop sharing. Cannot see the sharing. Screen. Okay, now you can see, right? Okay, remember when look at the truth table here. So this is 0 0 1 1 1 0 1 1, right? So I'll go back to the 0 0 1 1. So your result of x, y, z here, okay, and then with x z bar plus y, okay, is 0 0 1 1 1 0 1 1. Okay, 0 0 1 1 1 0 1 1. And then the combination is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1, and then 1 1 0, and then 1 1 1. Okay, and then you will build up the logic circuit. Okay, you will build up the logic circuit here. Okay, so based on the bit 1 1 1 1 1. Okay, so from the f functions here, you will get you will change back, okay, the combinations here. Okay, 0 1 0. Okay, because this bit is 1, so you will set the combination of x bar, y, and then z bar. Okay, so how do I know that which one it will be bar? If the bit is 0, then it will become bar. If the bit is 1, then there's no bar. Okay, so the function or the Boolean functions for this bit is x bar, y, z bar. And then this bit here is also 1. So x bar, y, z. And then this one is x, y bar, z bar. And then this one is one bit also, x, y, z bar. And then x, y, z. Okay, so that is the combination of functions. And then when we have the result, you will get I will combine it. Okay, I will combine it to get the result, which is x bar y z bar plus x bar y z, and then plus x y bar z bar, and then plus x, y, z bar plus x, y, z. Okay, so previously what we get the function is x, z bar plus y. And then when we do the truth table, okay, we combine it, we will get these long combinations. Okay, these long combinations. And then how do we draw the combinations? For example, if we have x bar, y, z bar, so your input will start as x, and then y, and then z. And then for the first combination, x bar, y, z bar means there's a long here, and then there's a not. Okay, so do we have a y bar? Yes, we also have a y bar also. So we will prepare it like this, and then like this. Okay, so next is that x bar, y, z bar. So x bar, y, z bar. So this is x, and then y. Okay, so y is here. Okay, and then z bar. Okay, so we need a z bar. Okay, and it, you will get x bar, y, z bar. And then the next one is x bar, y, z. Okay, x bar, y, z. So for x bar, y, z, so we will combine again. Okay, you will combine again with x bar, y, z. So here, so I will take a dot here, and then okay, another dot here. Sorry, another one. Okay, so I will take the dot and then cross here, and then take another dot and then cross here. Okay, so like this, and then like this. Then when I end it, it would become x bar, y, z, just like that. And then another, and another. So I will need to create another AND logic here, and another AND logic. So which is what might be, sorry, might be long. Okay, and then need extra gate for that. So continue with that. Do we have, it's supposed to be when we do the truth table here, okay, it complement each other. When I say complement means like this. So if we have the functions of x, z bar plus y, okay, so the value would be the same as this truth table. And from this truth table, you should get the same function of x, z bar plus y. But when we look at the result here, and then when I extract the combination, you will get x bar, y, z bar plus x bar, y, z plus x, y bar, z bar, like this, right? It's a long functions. So what happened is that we need to simplify back again. So go to the next slide. Oh my God, sorry. Go back. Here, this one. Okay, so we will go to the next slide, whereby when we want to do the simplification, okay, so we would follow a certain rules. Okay, you follow certain rules, right? For example, okay, since we have the combinations of functions after we do the truth table, right? So we will check on the certain rules that we can simplify. So this is the list of simplification laws that we can use. Commutative law. So the commutative law are applied to addition and multiplication. Okay, addition and multiplication. For addition, the commutative law states that in terms of the result, the order in which variables are odd makes no difference. Okay, it makes no difference. A or B is equal to B or A. Okay, so let's say if we, you can prove this. How do we want to prove that? using truth table. Okay, so it's only a matter of position. So if you look if you show the truth table, okay, A, B, and then another is B, A. So the position, okay, so the position would be 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then this one, okay, so this one is 0, 0, 1, 0, and then 0, 1, and then 1, 1. And then when you check the result, okay, both A or B is 0. This one is also 0. 0 or 1 is 1. This is also the same. This is also the same. This is also the same. So it means that A or B is equal to B or A. And then for multiplications, it's also the same. Okay. In terms of the result, the order in which the variables are ended makes no difference. Okay, makes no difference. So in this case, this is for OR. Okay, so this is for N. So the position change. So A and B and 0 and 0 is also 0. And then this is also 0. This is also 0. And then this is 1. So basically it is the same. So it is commutative law. So if you look at the Boolean functions and then you look at that there's a position is different, right? One of the formulas is ABC and then another is CBA. So can I arrange the result, the order of the variables? Yes. Okay, because of this commutative law. Okay, next is the associative law. So the associative law, when ORing more than two variables, when you have three variables and then you need to OR more than two, so the result is the same regardless of the grouping of the variable. Okay, so let's say when you want to try to factoring, okay, so I will teach you in certain ways. Sometimes you need to factor the variables. Okay, so when you want to factor the variables, so using this associative law, you can move. Okay, you can move the factoring. Okay, you can move the factoring here. So for example, if I want to change the ORing pair, okay, from B or C to A or B, okay, it is legal. It can be done. Okay, it can be done. So it's because of I want to try to pair something. Okay, I want to try to pair something. So I would move the pairing. So instead of, okay, you previously it was A plus B plus C like this. So I would like to pair with A plus B like this. And then plus C. And then do something after that. Okay, so we use this associative law. Okay, and then multiplication. Usually when we try to simplify, the ending is usually needs more the associative law actually. Okay, for example, A, and then we pair it, we group with BC, okay, and then close it, is also equivalent to A pairing B, AB pair with together, and then outside of the pair is the C. It is still N. Okay, both of the pairing here, okay, still use ending operation. This is also the same. Okay, A or B or C. Okay, if we remove this pairing, okay, it's still A plus B plus C. It's also the same with this one. A and then factor with the BC. Actually, if we remove the factor, it is the same as A and B and C. Like that. Okay, so why are we using this? So sometimes when you look at the combination, and then you have A, B, C plus A, B, C bar, like that. And then you want to use the pairing, so you will use the associative. Okay, you will use associative, and in this case, what we have is the combination of A, B, and then we want to pair with C plus C bar like this. Okay, no, this is not good. This is not a good example. No. Let me change. Not good, not good. Okay. Okay, right. So you want to pair something, right? So, and then, okay, A, B, C, like that. And then, plus, okay, A, B, like that. Why is it coming like that? All right, so like that. So it's like that. So one is A, B, C, and then plus A, B. And then what you want to do is like, you want to pair with A, B here. So what you do is, you move the pairing, you move the you move the grouping. Okay, so A, and then pair, and then grouping the BC. So, okay, A bracket BC. So we move the bracket to become A, B bracket, and then C. So we can do this using this associative law for multiplication. Right. Alamak. Okay, forgot to check the comment. Okay. And then distributive law. The distributive law is the factoring law. Okay, so a common variable can be factored from an expression used as in ordinary algebra. So that is, if we have AB plus AC, so we can see that A is the same. Okay, A is the same variable. So we have the same pairing of variable, which is A. And then the difference that we have is B and C. So what we can do is that we can factor the variable A here, okay, and then group, okay, the variable that is not the same. So from AB plus AC, okay, we can factor it to become A bracket B or C. Okay, so it's the same as this case, A, B, C plus A, B. Oh, I say, man, not so. I really don't like it. Okay, let me draw back again. Hold on. So A, B, C plus Bismillahirrahmanirrahim. Okay, A, B, C bar. Okay, so now, what variable that is the same between these two terms? Between these two terms, A, B, C plus or A, B, C bar. What is the same? What is this? Which variable that is the same and we can factor out?
AB.
AB, yes, correct. Okay, AB. Okay, so AB, we factor out. Okay, we put it as the main factor, and then the grouping would become C plus C bar, like that. Okay, so there's a reason when we put that, and then there's a certain, there's other laws that can cancel this out. Okay, so you will see it later on. Okay, so the distributive law is a combination of N, and then OR. Okay, so you need to look at the combination, which one can be applied for the distributive law. And then when we draw the logic, okay, when we draw the logic, okay, so this one on the right figure, okay, use A and B here, this one, A and B, and then A and C, and then combine the result of AB and AC, okay, so you will get, combine with all logic, so you will get X. And then the other logic, okay, the other functions is B or C. Okay, which one we need to draw first? You will draw inside with the bracket. Okay, so the bracket is the first priority. So the although N is higher priority than OR, But since we have bracket here, so bracket will become the higher properties, higher priorities. So B or C, okay, B or C, and then the result we will end with A. Okay, so we will get the functions of A bracket B plus C. Okay, so the figure looks different. Okay, the figure looks different. So what's the difference? What's the difference? What's the difference? You can type or you can speak. So what's the difference between this left side and the right side figure? No answer. Tembak saja. Just try.
The get logic they use, madam.
Yes. How many logic for the left side and the right side?
The left side has 2. The right side has 3.
Okay. So now there's a difference there. So even this is like a circuit, but actually it was implemented on the circuit board. So yes, it doesn't have not. Okay, it's because of the function was not there. Okay, so if there is a not, then you need to calculate the not also. Okay, so not is usually represent with like a small circle dot. Okay, small circle. Okay, small circle. So if there's a small circle, then you need to calculate that gate also. So in this case, the left side here use 2 logic gates, and then the right side here use 3 logic gates. But both have the same result of truth table. Okay, they have the same truth table. But the difference is the number of gates that is required. And as we can see, okay, the more gates that needs to be soldered in the circuit board, the higher the cost. Okay, they increase the cost. So when they design the circuit board, they have to calculate. They have to calculate the circuit, and they have to calculate the circuit cost and also the performance. Okay, even if I said that the right side require more gates, but there's a certain conditions that says that if there is a more circuit here, there's a more logic circuit here, it is much cheaper, okay, than the other functions. Okay, so I will tell you which one. Okay, so but for a simple logic like this, okay, so it is still preferable if we can use the logic and logic or and logic not, because it's very cheap to apply it. All right, so I've teach you only 3, right? Because there are a lot of rules that we can apply for you to simplify. Okay, so for this chapter or for this week, you need to learn how to simplify Boolean functions. Okay, Boolean functions. So previous is commutative law and then distributive law. Okay, now we will learn an extra another 12 rules here. Okay, so okay, my pen is here. Okay, A or 0. Okay, A or 0 is A. Okay, and then A or 1 is 1. Remember when we do OR, it is the same as sum. Okay, it is the same as sum. So we don't know A, value of A here. So A can be 0 and then A can be 1. So if A can be 0 or 1, then the rules here said if A plus 0, then the result will be A. We can simplify as A. And then if A or 1. Okay, so remember, or sometimes can be a sum. So if there is 1 here, okay, you can simplify as 1. We can cancel A here. Okay, so it will leave as 1. Okay, that is for or. Okay, for N. Okay, for N, A and 0, it's always 0. Okay, so for example, if I write ABC dot 0, or it's always 0, it's always 0, or we can say A, B, and then 0 here. So remember, if there is a grouping there, that like a bracket, so it means that A and B and 0. So it's equivalent to 0. So you can just cancel out like that, so become 0. Okay, so that is how you want to simplify the Boolean functions. All right, and then if it's A and 1, okay, so we can simplify this to become A. So like this. It's not cancelled. It's hidden there. Okay, for 1 there, it is hidden. So as I said before, if it's like this, A1, Allahu Akbar. Hold on. My pen is making a prank on me. Okay, hold on. So A, Bismillahirrahmanirrahim, dot 1. Okay. Okay, so it's equivalent to 1. So let's say my value is 1 here. So I can also represent it as A1 or 1A. Okay, so 1 here is hidden. You cannot see it, but you can simplify it. Okay. As for this one, A dot 0, it's not hidden. It's totally 0. Okay, the A here will be cancelled out. So it's not, for this case, 1 here is not cancelled, but it is hidden. Right. Okay, and then for the A plus A, okay, so A plus A or A means we can simplify to become 1A. And vice versa. It can go back. You can say if A is equal A or A, so you will get the same truth table. You will get the same truth table. So this is or. Okay. So 1 here, is it equal to 1 or 1? Yes, true. Okay. So A plus A is equal to A, and then A or A bar. A or A bar is equal to 1. Remember, when this one is inverse, let's say this is 0, when it is inverse, it will become 1. So 0 or 1 will become 1. And then let's say A is 1, and then A bar is 0. So 1 or 0, you will get 1. So that's why A plus A bar is equal to 1. Okay, so remember when I put a bracket there. ABC plus ABC bar, right? So, and then you use the distributive law, right? So, A, B, C plus C bar. Okay, so it's in a bracket. So, now you see C plus C bar can use these rules. Use rule 6. Okay, use rule 6. A plus A bar is equal to 1. So you will write A, B, bracket 1. Okay, so bracket 1. So what happened? If A, B, bracket 1 is equivalent to A and B and 1. So follow rule 4. Rule 4. Rule 4 is equivalent to, no. A dot 1 is equal to A. So what we have is A, B. The 1 is hidden. Okay, the 1 is hidden. So now can we simplify it again? No, you cannot, because A and B is not the same. So it's already simplified. So that's what I mean. Okay, next. Let's look at the rule 7. Rule 7, okay, A and A is A. Okay, A and A is A. So it's the same as also for the rule 5. A or A is equal to A. So I can say A plus A is equal to A. You can also say A is equal to A plus A. Or for example, for example, if we have AB, so you can say AB plus AB, like that. Okay, so following the same rules, rule 7, if A dot A is equal to A, then it can be reversed. So A is equal to AA. Or I can just write AB is equal to AA BB or AB AB, like that. Okay. So you might want to ask me, Madam, why are we doing the something like doubling the numbers? There's a reason. Okay, when we do the simplification, you need to expand. Okay, you need to expand the bit. So in this case, usually this type of logic now is starting to make prank. Cancel, cancel, cancel. Cancel, cancel. Okay, so now, for example, for this one, so A is equal to AA, like that. Okay, so sometimes, okay, there is like a function like this, A plus AB. Can I simplify it like that? So there's a certain things there that you need to do. So I would try to expand it. So AA plus AB, like that. Okay, so and then there's certain operations that you need to do. So sometimes A here needs to be expand. So you expand to become two variables, okay, of the same value. Right. So that is for rule 7. For rule 8, A and A bar. So here means that if A is 0, then A bar is 1, so it's totally 0. And then if A is 1 and A bar is the opposite of it, which is 0, so you will get also 0. So these rules means that if A dot A bar, it will cancel out. So like this. I say main. Hold on. Alright. Where's my pen? Okay. For example, let's say we have a combination. So A like this, AB plus sorry, no, not plus. No, plus, not plus. Hold on. Not plus, we want to use n. Okay, so that's a combination. When you do the combination and then AB, A bar, like that. Okay, A bar, C, like that. So when you see this combination, one is A, one is A bar. Okay, so one is A bar. So we use this rule 8. A dot A bar is equivalent to 0. So you can cancel out. Okay, so this one is cancelled because it says 0. Right, and then A double bar. Okay, one is one is 1 bar and then another is a double bar. So if it's a single bar, means that it inverse. Okay, it will inverse the original value. But if it is a double bar, okay, double bar means equal to the same as the original one, means that they will cancel out the bar. Okay, so in this case, A double bar is equal to A. So let's say A is 1. So when you first bar, okay, so when first bar it is 0 and then we bar back again. Okay, we inverse back again, you will get 1. Okay, so that's why double inverse is the original one. Okay, you will get the original value. Okay, so for example, we have A, B like this, and then there's a bar there, so it is equal to A, B. Okay, but there's a difference. Okay, but there's a difference between A like this and then be like this between A, B, full bar. Okay, A, B, full bar. So, let's say if you have A and then B and then small bar here and then you have a full bar there. You have a full bar there. You cannot simply say that this is A, this one, and then like this. No, it's not. Okay, it's wrong. Okay, there's a difference there. Okay, even if you use the truth table, you won't get the same answer. Okay, you won't get the same result. So this one only applies for a single variable. Okay, this one will apply on a single variable, except that if you use a long bar here, okay, so it applies on the same variable. Then we can cancel out. For example, this one, AB double bar. Then you can cancel out to become AB. Okay, so and then if you want to ask, okay, whether if we have A double bar and then B bar here, and then B bar here, so can we cancel out, can we change A here, A double bar to become A? Yes, correct. It's because of the single variable. So here, if A double bar and with B bar, so what you get is A and B bar. Like that. Okay, so that is for rule 9. And then rule 10, A plus AB or is equal to A. So A plus AB. And then how do we get A here? So remember when I said that A here, okay, can be expand. So can be expand. Okay, so use rule 4. Rule for this one. So we can say A1 plus AB. A here, A is equal to A dot 1. So I would use A dot 1 plus AB. So can I factor out the value? Can I factor out the value? Yes, you can. A, because we have A here, so, and then we will factor 1 plus B. And then, so next, what would be, which rules should I apply when I have 1 or B? 1 or B. Which rule should I apply?
2.
Okay, laju aja. Okay, yes, correct. Okay, rule 2. Okay, rule 2 is A plus 1 is equal to 1. So, A plus 1 is equal to 1. So, what we get is A1. And then, if this is A1, which rule should I apply?
4.
Yes, rule 4. So, A1 here is hidden, has been simplified to become A back again. So that's why the rules here is a combinations of several simplification rules. Okay, so A plus AB is equal to A. Okay, and then you might want to ask me, Madam, if we have 1 plus B plus C, okay, plus D, can we simplify it as A plus 1 is equal to 1? Yes, correct. Yes. Correct. Okay, you can simplify it. Okay, you still can simplify it like this. 1 plus B is 1. And then 1 plus C is 1. And then 1 plus D is 1. So, in a short way, you can say 1 plus B plus C plus D is equal to 1. Okay, so that is for the rule 10. And then rule 11. Rule 11 is A plus A prime B. Okay, if I say A bar, the sound after that doesn't sound good. So I would use, sometimes I would use prime, sometimes I will use bar. Okay, so just flip in your mind, this is an inverse. Right, A plus A prime B is equal to A plus B. So the Okay, the simplification. Let open my notes. This one. Kat mana? Ni. The name is absorption law. Okay, where is this one? Which one? A plus A prime B. So A plus A prime B is equal to A plus B. So so the law that they use is that the A plus A prime B, they would use the previous one. Okay, they will use the previous one, A plus AB. Okay, A plus AB. Okay, which one? Which one? This one, A plus AB. Okay, A plus AB is equal to A. Okay, so let's okay. A plus A prime B. Okay, so we can say that A here, okay, we use rule, not rule this one. Okay, we will use rule 10. A plus AB is equal to A, right? So, A plus AB is equal to A. So, we can reverse A here to become A plus AB plus A prime B. Like that. Okay. So now we have expand back again. Okay, you have expand back again. And next is that, look at this. Okay, so A plus AB here plus A prime B. So means that you need to expand the A here. Can I expand it to become double A? Yes, we use the rule, which one? This one, rule 5. Okay, no, not rule 5. Which one is A dot A? A dot A. This one, rule 7. Okay, rule 7. So we use rule 7. Rule 7. A is equal to AA. So what you get is AA plus AB plus A prime B. Okay, right? Now, so what you can, from here you can see a pattern. Okay, because we want to simplify this A prime, right? So A prime here can be combined or can be grouped with this A. So the only similarity is the variable B. So what you have is AA plus, you can factor B and A plus A prime. Okay, A plus A prime. So which rule is it? I need to look at the notes. Hold on. So, not this one. A plus A prime. This one. Rule 6, okay? Rule 6. Okay, so rule 6, A plus A prime is equal to 1. So, here you have AA plus B1. Okay, so you can say that rule, which rule is it? This one, rule 4. A dot 1 is A. Okay, A dot 1 is A. And then rule 7. Rule 1. Okay. Sorry. Which rule is it? Rule 4. So rule 4, A dot 1 is equal to A. So what you have is AA plus B. Okay. So what about A here? Can we simplify? Yes, you can use rule 7 is A dot A is equal to A. So what you have is A plus B. Okay. So that's the simplification for the rule 11. Okay, rule 11. And then for rule 12. Okay, rule 12. I also followed the ni. Hold on. Let me show this slide. This one. It's called distributive law reverse derivation. The name is too long, but usually what I remember is the result. Okay, so if I have A or B, and then we end it. You end it with A or C. Okay, A or C. First is that we do the we remove the bracket. Okay, so when we remove the bracket, it's like we do the multiplication. Okay, we do the multiplication. A plus B, A plus C. Okay, so like this, A plus B, and then ended with A plus C. So what happened is that we like multiply 2 times to this one, and then 2 times to each other. So we expand, okay, to remove the bracket there, it's because of between the bracket is the AND operation. So it's very hard to multiply it. It's very hard to remove to simplify it. So we need to expand the the bracket. So to expand the bracket, then we need to multiply. So A multiply by A and A. So you will get A, and then plus AC, and then this one B multiply by A. So AB. Okay, it's because BA is equivalent to AB, right? So it's also the same as BC, like that. So now what we have? What do we have? So we have AA plus AC plus AB. So can we simplify it? Yes, you can. As you can see here, we have AA, AC, and then AB. What variable or what formula that we can use? Which formula that we can use? This one. Okay, between okay, so this one. Where's my pen? My pen. Okay, so now we have AA plus AB plus AC. So which rule that we can apply? Which rule that we can apply? Which rule we can apply?
Rule 7.
Rule 7.
7.
Don't use that. Don't simplify that one first. We need to do, compare it AA and AB, and then AA and AC. Which one? We can okay, between AA and AAAB, okay, and then AAAC, can we use any rules that we can simplify?
Rules number
10. Rule 10.
Rule 10. Correct. Rule 10. Yes, correct. So, let's say AA here you want to simplify to become A. So, let's say A here is rule 7. So, you will get A plus AB and then plus AC. And then now, you have A plus AB and then A plus AC. So, we can use rule 10, right? We can use rule 10. So, how do you want to use rule 10? Okay, now, let's close back again. Where is my pen? Okay. So now what we have is that AA plus AB plus AC is we use rule 7. A is equal to A. So here is A plus AC plus AB plus BC, like this. Okay. So it's equal to A plus AC plus AB. So rule 10. You said, okay, rule 10. A plus AB is equal to A, correct? So we will pair with this one. So A plus AB, like this. and then plus AC plus BC. And then we can get A here. Okay, so A plus AC plus BC. Now, which rule we can use to simplify again? The similarity between, yes, A and AC, so we can still use the A10, rule 10. So, rule 10 is A plus AC, A plus AC is equal to A. So, what we have is A, and then plus, what's left is BC. A plus BC. So, can I simplify by again? No, because B and C is a different variable. Okay, so B and C is a different variable. Ni, see? So, there's other style of how to simplify it, but basically we will get the same result. Okay, we will get the same result. So basically, it's the same. So now, A or B factor with A or C. So we will get the simplification as A or BC. Okay, so you just need to remember the formula. You don't have to remember the number of rows. No, you don't. Okay, so this is the basic rules that you can apply for all of the simplifications. Okay, and then only that. Okay, so if there is more, usually it comes with the combination of the previous simplification rules. Okay, so usually we will use that all these 14 rules. Okay, so let's continue with the ada orang komen ke? Hold on. Oh no. Okay, so Boolean identities. So that's another rules or theorem that we can use. Okay, right. So the complement of two or more ended variables is equivalent to the OR of the complements of the individual variables. So this is what we call as the De Morgan's. De Morgan's is because we have a full bar at the combination of the variables. Okay, so if we have a full bar of the combination of the variable, then we can use the De Morgan theorem. Okay, full bar here is not good to it's very difficult to simplify. So the easiest way is that we break the full bar. Okay, you break the full bar here. So this is a full bar of A, B, and then there's a full bar there. So we need to break down this bar. Okay, so using the De Morgan's theorem, okay, so to break between A and B full bar, so since this is an operation of n, so when you break it, okay, it will become OR. Okay, it will become OR, and then each of the variable will have a small bar. So A bar and then OR with B bar. Okay, so that is if the full bar is under the AND operation. Okay, next, if the complement of two or more odd variables means that the full bar is for OR operation. So A or B and then full bar. So now you want to remove the full bar. Okay, so when you want to remove plus here, change to n, and then the variable will become a small bar. So A bar and B bar. Okay, so that is how you want to break out the full bar here. Okay, so that is the simplification. So and then how do you want to prove this? Okay, sometimes the question asks you, how can I prove that AB full bar is equivalent to A bar plus B bar? Okay, so how do you want to prove this? Using truth table. Okay, so to prove this variable, what you can do is, okay, just list out A, B like this, and then 0, 0, 0, 1, 1, 0, and then 1, 1. And then do the operation of AB and then AB and then full bar, and also A bar or with B bar. Okay, so when you do the operation A and B, okay, A and B is a 0 and 0, and then we bar it is equal to 1. And then 0 and 1, okay, 0 and 1 is equal to 0, we bar it is also equal to 1. And then this is also the same, 1 and 0 is equal to 0, bar it, we will get 1. And then 1 and 1 is equal to 1, we bar it, we will get 0. Okay, as for this, A bar plus B bar, right? So 0 bar plus 0 bar, okay, so means that this is 1. Okay, and then 0 bar plus 1 bar is equal to 1. Okay, it's because of 1. We OR it with 0. So at least 1 bit is 1. Then you will get result 1. And then 1 bar plus 0 bar is also 1. And then 1 bar plus 1 bar is equal to 0. So as you can see, both have the same result. So this is equivalent proof. Okay, it's the proof that both sides will produce the same result. Alright, so when we do the truth table, okay, and then we will extract the Boolean expression. Okay, you will extract the Boolean expression. So the Boolean expression can be written in the sum of product or in the product of sum. Okay, so an expression in SOP form when two or more product terms are summed in the example such as this. Okay, so it starts with the combination of n first and then we sum it. So A and B, okay, sum with A and B and C. And then it's also the same as ABC or CDE or B bar, C bar and D bar. So this is what we call as SOP. Okay, so how do we derive SOP expression? Okay, how do we derive SOP expression? It's based on the output of the truth table with the value of 1. With the value of 1. So, how do I extract that? Okay, so how do I extract that? Okay, so let's see. We have X, Y, Z, and then so I don't know the functions. So you will be given a truth table. So this is the F, which is the output. So your combination is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now I don't have the functions, but the result will be given to you. So what would you get is 0, 0, 1, 1, 1, 0, and then 1, 1. Like that. Okay. So now, how do I simplify it? You need to extract the expression. You need to extract the expression. So usually the simplest way is to use the SOP expression. So the SOP expression is that we take out, okay, from this variable as it is, okay, as it is. So SOP will look at the result, okay, the product of the combinations, value binary 1. Okay, if the value is 1, then we will take out as the SOP expression. Here, this one. Okay, so this one, this one, this one, this one, this one. Okay, so this will become your SOP expression. And then look at the combination 0, 1, 0. So we will convert 0, 1, 0 to become a variable. So 0 will become a bar to that variable. 1 means that the normal variable. Okay, normal variable. So in this case, 0, 1, 0 can be expressed as x bar, y, z bar. So this is SOP. So is there more for the SOP? Yes. This one is x bar, y, z. And then x, y bar, z bar. And then this one is x, y is because of 1, 1. And then z is 0, so we put a bar there. And then the last one is x, y, z. And then do we complete it? No, not yet. You need to combine all. F. So since this is a product of n, okay, so for each of the term, we call this as term. This is a term, okay. So this is a term. So we combine each term, x bar, y, z bar, combine with OR. Okay, combine with OR operation. So x bar, y, z plus x, y bar, z plus x, y, z bar plus x, y, z. Okay, so this is SOP. So this is SOP. Okay. So this is a combination for SOP, and then for POS. So an expression is in a post form when two or more sum terms are multiplied, as in the following example. So it's like this. Okay, your expression inside the bracket is the OR operation, A or B. We product, okay, we multiply or product with another term, A or C. And then we multiply again, and then next. Or we another example is A or B or C bar, and then product with B or D. So this is quite difficult, right? If you want to simplify it, but there's a condition when post is better to use compared to the SOP. Okay, so how do we form the post expression? Based on the output of 0. Okay, output 0 means that, okay, let's say express the Boolean expression using POS. Okay, so POS, okay, POS will use the result 0. Okay, let me erase this part first, and then for POS, we will use value 0. Okay, we will use the result 0. So the result 0, we don't simply do the the SOP, but instead of, we will OR it. We will OR it like that. So here, the combination of variable is x 0, 0, 0. So for post is the opposite of the SOP. 0 here means the neutral one, the positive one. So here you will represent as x plus y plus z. And then for this one, okay, this is a 0, 0, 1. So 1 here means bar. So you will express in the post form x plus y plus z bar. Okay. And then for this one, this is 0, right? So 1, 0, 1. So x bar plus y plus z bar. Okay. Now, expression f in SOP form is we combine. So x plus y plus z, we put a bracket to multiply with another term x plus y plus z bar. And then and again with x bar plus y plus z bar. So now this is in post form and this one is in SOP form. Okay, now you have both. You understand? Can you do this on lab? You should. Okay, you should. So now let's continue. Okay, so where's my side? Where's my side? Where's my mouse? Okay, now let me continue back again. Allah Akbar. Okay. Okay, so now. Okay, so logic simplification using Boolean algebra. Logic expression can be reduced to its simplest form or changed to a more convenient form. For example, we have AB plus A bracket with B or C, and then plus B bracket with B plus C. So in this case, we want to eliminate the bracket here, whereby you can compare with you can pair it with the other terms. So here we use distributive law. So to remove the bracket. So A and then factor with B plus C. So we distribute to become AB plus AC. And then this one also BB plus BC. And then use the rule 7, A dot A is equal to A. So what we get is BB to become B. And then now we have AB plus AB. So we use rule 5. A plus A is equal to A. So this one would be cancelled out. Okay, so we can remove that in the expression. So AB, what's left is AB plus AC plus B plus BC. So remember, okay, when you look at B plus BC, it's actually B1 plus C, right? So B1 plus C is actually equivalent to B1 and equivalent to B. So they will use the expression rule 10, A plus AB is equivalent to A. So here, B plus BC is equivalent to B. So we use rule 10 to simplify B plus BC, and then for AB plus AC. So now, we will use B plus AB. Remember, B plus AB to use the same rule of rule 10. Okay, to use the rule 10. So what you can get is B plus AB is equivalent to B, and then plus with AC, and then there's no more to be simplified. Okay, so this is how we use the simplification using a Boolean algebra. Another technique to simplify it is by using Carnot map. So the Carnot map uses an array of cells to represent binary values of the input variables. Okay, so the number of cells in the Carnot map is equivalent to the total number of possible input variable combinations. Okay, in this case, the number of cells is determined by using the formula of 2 power of n, where n is the number of inputs of variables. For example, z is equal to a and b. So now, determine the number of variables. We have variable a and b, which means 2 variables, right? So the combinations of cell, okay, the combinations of cell is 2 times 2 power of 2 input. Okay, this is input. So 2 power of 2 inputs is equivalent to 4 cells needed to represent the Carnot map. So to represent the Carnot map, since we have 4 cells, it will become like this. Okay, so let's say we have combination of x, y, z, means that 2 power of 3. So your cells is 8, right? So to combine the cell, to represent the cell in 8s, okay, so you can have 1, 2, 3, 4, 5, 6, 7, 8. here is X, Y, and then this one is for Z. Okay, so here is 0, 0, 0, 1, 1, 1, and then 1, 0. So it's not like the combination of the sequence 0, 0, 0, 1, 1, 0, 1, 1. No. Okay, the sequence must be there's a contiguous bits. Okay, there must be a contiguous bit. Okay, between the cells. Okay, between the cells. So in order for you to simplify between at least one variables. So here, okay, for XY, okay, if the combination has two variables here, 0, 0, and then the next bit, okay, must have a contiguous or the same bits. Here 0, 0, and then 0, 1. The bit that is the same is this bit. Okay, bit X. Okay, 0, 0. Okay, and then for the next one, okay, usually when we arrange it in sequence, if it's 1, 0, so you will see 0 change to 1 and then 1 change to 0, means that there's no it's not contiguous. Okay, it's not very near, we cannot simplify it. So we arrange back. Okay, we are not using 1, 0, but instead we use 1, 1. So 1, 1 here means that Y here is 1, and that another cell here is also 1. The only difference is on the X one. Okay, so they change value from 0 to 1. Okay, so that's why the flip bits, okay, the bits that change at least one bits only. Okay, so the changes happen is only on one bits. Okay, it's also the same from the last one, 1, 0. Okay, from here, X is 1. Okay, on the next cell, X is also 1. The only difference is on the Y. So Y is 1. Another cell is Y is 0. Okay, you also can represent this using expression. X bar, Y bar, X bar, Y, and then X, Y, and then X, Y bar. So if you want to simplify it, at least one variable must be in the same state. Okay, so let's say if we want to simplify between X bar, Y bar, and X bar, Y. So X bar, Y bar plus X bar, Y. At least this X bar is the same, right? So X, guys, did you hear my voice?
Yes,
Yeah.
madam.
Okay. It's because of on my monitor it says that network quality is not good. So if my voice missing, please tell me. Okay, let's continue. So since we have X bar, Y bar, or with X bar, Y, so we can factor it to become X bar, Y bar plus Y, like that. Okay, so this is how we simplify using the Carnot map. So the position, okay, the position of the cells must be in the state of 0, 0, 0, 1, 1, 1, 1, 0. Okay, so that is for bit 8-bit cells. 8-bit cells. Okay, what about 2 power of 3, 2 power of 4? Okay, 2 power of 4. You will see it later. I will show it to you. Okay, I will show it to you. Okay, now the process of simplification using the Carnot map, or what we call as minimization, resulting in an expression that contains the fewest possible terms with the fewest possible variables. So after mapping the SOP expression into the Carnot map, the next step to produce a simplified SOP expression by grouping the ones. Okay, by grouping the ones. The rules is that you within the group of bits. Okay, so one group can only contain 1 bits, or maybe 2 bits, 4 bits, 8 bits, or 16 bits. which is based on the power of 2. So this is a power of 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3, and then 2 power of 4. So if you group a bits of 6 bit, 10 bits, what else? 6 bit, 10 bits, 12 bits, that's wrong. You cannot simplify that. Okay? So when you want to simplify, you find out if there is a similar adjacent 2 bits of 1, 4 bits of 1, 8 bits of 1, or 16 bits of 1. Okay? Or at least if there is no group, then put it into 1 bit. Okay, 1 bit to become 1 group. So each cell in group must be adjacent to 1 or more cells in the same group. Okay, and then the first step is that you must group the largest one and follow with the other group if more group can be identified. So look at the biggest one if there is a 16 bit of 1, and then if there is none, we look at 8 bit one, and then if there is none, and then look at the 4 bit one, and then lastly 2 bit one. Okay, if there is no 2 bit one that can be grouped, then we can just group into 1 bit. Okay, so make sure each one of the map must be included in at least 1 group. Okay, you must group it in at least 1 group. Okay, so the ones that has already in a group can be included or can join to another group as long as the overlapping group include a non-common ones. Okay, so how do I get this Kano map or bits here? Okay, so how do I get that? Let's go to the okay. So remember this. Remember the truth table. So let's. Okay, so I have the expression here, right? So, do I need to let me. Okay. I hope you can see it. So now, let's say we have 8, right? We have 8 combinations because of we have 3 variables. Okay, x, y, z means 2 power of 3, which is equal of 8 cells. So to have 8 cells, you will draw like this. Okay, you can draw like this. Okay. Or whichever you like. Okay, whichever that you like, you prefer, is basically the same. Both way can be done. Okay, both way can be done. So the only thing is that you need to label it correctly. So you need to label it correctly. So let's say if you are using this side, okay, so this side, so this would become x, and then this will become yz. As for this one, this is xy, this will become z. Okay, so the combination is this is 0, this is 1, this is 0, 0, 0, 1, 1, 1, 1, 0. And then this is 0, 0, 0, 1, 1, 1, 1, 0. And then this one is 0, this is 1. Okay, and then when I try to map back again, use the truth table. Use the truth table here. Look at the result. So just look at bit 1. Okay, Kano map always use the SOP expression. Okay, Kano map usually use SOP expression. So we look at bit 1. So bit 1 here is 0, 1, 0. So look at the 0. Start with X. 0 and then 1, 0. So 0 and then combine with the left side 1, 0. So this is 1. And then 0, 1, 1. Okay, so 0, 1, 1. So 0, 1, 1. This one. And then 1, 0, 0. So means that X is 1, 1, 0, 0. And then 1, 1, 0. So 1, 1, 0. And then 1, 1, 1. 1, 1, 1. Okay. So let's say you said, madam, can we do the vertical one? Okay, let's do the vertical one. Okay, so 0, 1, 0. So 0, 1, 0 is here. And then 0, 1, 1 is down here. And then 1, 0, 0. 1, 0, 0. This one. And then 1, 1, 0. So 1, 1 is X, Y, Z bar here. And then X, Y, Z. So 1, 1, 1 is here. So it looks different. But when you try to do the grouping, basically you will get the same result. Okay, so let me zoom back again. Now. So to group it, okay, to group it, remember the first rule. Remember the first rule. Find the biggest cells. Okay, find the biggest cell based on power of 2. So the biggest cells start from 16, 8, 4, 2, 1. So what's the biggest cell that you can group? What's the biggest cell that you can group? Just guess, just guess. Just guess. No problem if you got it wrong. No problem. Just guess.
16.
You have to count the bits. You have to count the bits. Okay? So the size, follow the size. We have 8 cells, right? We have 8 cells. And then the rest, okay, I just put a bit 1 here. So the rest will become 0 there. Okay, the rest will become 0. So now, when we try to group, we look at the number of bit 1. Look at the bit 1 here, and then look at the a group of bit 1s that we can make a circle. That you can make a circle. For example, look at this one, on the left side one. Look at it on the left side one. So look at the left side here. This one, this part. This one. Okay. Look at the bit 1 that we have. 1, 2, 3, 4, 5. So what is the biggest bit that we can circle based on these rules? Based on rules 16 bit, 16, 8, 4, 2, 1.
4 medium.
Yes. 4. Okay, look at this bit. We have 5, right? We have 5 bit 1. So basically, it's not 16 or 8. So we look at this. Okay, we have 5 bit 1, but 5 is not a 2 power of something, right? So we said, okay, 4. Does the 4 is adjacent to each other? Okay, does the 4 adjacent to each other? So if you look here, bit 1 here is opposite to this side and also to the other side. And then this one is also adjacent to each other. This one is also adjacent to each other. Okay, if you see it like this, then I can group it to this circle. Okay, now, how many bits left? How many bits left? How many bits left? 1, right? So can I group this 1 bit? So if I want to group it, how many bits that I can group with this bit 1? How many bits that I can group with this one? Is it, okay, so you normally you will see it like this and then you will just group it like this, right? Okay, now that's another way. If you look at the, okay, if you look at the position, okay, so actually, okay, actually the bit 1 here, okay, is adjacent to this bit. It's like how do I say? It's like a round robin. This one. It's like this. It's like a round robin. Okay, so like this. So you can say that 0, 0 here is adjacent to the 1, 0. It's because of the bit y is adjacent to this bit y bar here. Okay, on the other side, at the other end. So it's also the same for here. Okay, for bit 0, 0. Okay, 0, 0 here for z bar is adjacent with the z bar here. So you can see y bar, z bar is adjacent to the y z bar. So the same z bar. So it's like a round robin, which means that they can be paired. So if I can pair it, so what I can circle is like this. I would circle like this. Kejap. My pen. And this. So when you combine, okay, this is 1/2. Okay, this is another half. So then you will get a full circle of 2 bits. Okay, so this means there is a 2 bits here. So what about this? Okay, basically you will get the same style. This one is much easier, right? So now this is a 4 bit because they are adjacent to each other. Okay, and then there's a 1 bit here. You can just there's a single bit here, but actually there's another rule that said if 1 bit here has been borrowed or has been in another group, we can group it to another. No. I have to use other colors. Use other colors, So we can group with another bits, okay, with exception, okay, on that circle, at least 1 bit is not in another group. So in this case, this bit is not in other group, solely on this green group. Okay, and then for the blue group here, okay, although this bit has been used 2 times, but the other bits is not in another group. So they are solely under blue group. Okay, so remember, okay, at least when you have a duplicate or a redundant bits here, okay, on this bit here, there's a redundant bits. So make sure, okay, at least on that circle, at least there is 1 bit that is not redundant. Okay, so that is the that's the rules. Okay, so that's the rules. And then look back again. Is there any bits that is left? No. Okay, so there's no more bits left. Then we can label it. Okay, you can label it. So in this case, we label the big first. Okay, the big circle here. Let's use the blue color. Okay, let's use this one. Okay, now how do I circle it? Okay, how do I circle it? So okay, let me finish this part. All right. First is that I would label it back with the variables. So here 0, 0 is y bar z bar, and then this one is y z, and then this is y bar z, and then this is y z bar. And then for this one, this is x bar x. Okay, so x bar x. So okay. So based on this column, we look at the column first. For this blue group, okay, it will expand from 0 to 1, from x bar to x. Okay, from x bar to x here. So when they expand until these two sides, okay, because the group here, okay, until this part, x bar and x. So imagine x bar plus x is equal to 1. Means that we cancel it. So here, so x is not included in the expression. So x is not included. So what's left is the y and z. So why? We look at the row y bar and yz and yz bar. So between yz and yz bar, okay, the only variable that does not change, between yz bar, yz and yz bar, the one that's changed is the bit z, right? So what's left is only y here. Okay, what's left is only y here, and then that's it. Okay, that's it. Because x is already cancelled out. X bar 2x, so no more x here. And then between z, okay, so z to z bar is also cancelled. So what's left is only y. Okay, next is the bit two groups, two bit groups here. So let me. Okay, now, okay, two bit groups here is between y bar, z bar, and y z bar. Okay, but the column is x. Okay, column is only on x, so it doesn't exceed to x bar. So since the column doesn't change, so it's only x, so then we can just write x only. Okay, x only. And then the row is between y bar, z bar, and then y z bar. So which variable that's changed? Which variable that is changed? Y bar, z bar, and y z bar. Okay, between this bit and between this bit. So y bar, z bar, and then y z bar. So which bit that's changed? Which bit that is changed? From 0 to 1 and then 0 to 0. Which one? Tell me. Dah, tak ada jawapan. Semua dah tidur.
Why?
Y. Okay, so Y changed, right? So because Y changed, so we will not write the Y. So what's left is Z bar there. So since Z bar left, so now we have finished it. So then you can write F is equal to, combine all of this. Okay, so we have Y plus X Z bar. Okay, or we can say X Z bar plus Y. So when you compare with the previous one here, so you will see that you can see that okay, it's the same. Okay, so it will be the same. So to know that this is the correct expression, use a truth table. Okay, use the truth table and then simplify using Boolean algebra. So that's it. Okay, so we will finish with the Kano map and then do the exercise next week. Okay, so I will see you next week. Yes, I know. I'm finishing it now. My clock there still 3 minutes. So okay, let's finish now. Okay, I'll see you next week. Bye. Assalamualaikum.
Thank you, madam.
Waalaikumsalam, madam.
Thank you,
madam.
Salam, madam. Thank you, madam.
You're welcome.
madam.
Bye. I will end it. Okay, I will end it. So it's okay. You just end. Okay, you can leave now. Okay, bye.